presenter, and Sean's going to be driving it for me here. So just a second as he gets his screen up for me. So thank you. Just a quick note, Cole Widener, Siemens Process Instrumentation, technical sales consultant. So why are you talking to me? I'm basically a field engineer who supports Ponton and goes out into the field and helps with the technical aspects of measurement in applications. I'm available to be on site, but in these current times, it's probably more so available for web-based stuff. Sean and I have very similar careers, but I spent most of my career as a flow product specialist, while Sean has a lot of pressure knowledge. So I'm going to go over some of the basics and really turn the bulk of this pressure stuff over to Sean. But like I said, I wanted to be on this, wanted to have the opportunity to talk with all of you on some different applications, and be a second point of contact. Basically, Josh is your main guy. You could contact me on anything, and just leave Sean in there as well. But his responsibilities often take him elsewhere than talking to customers every day. But we are here for technical resources, and then as we're going to do some questions at the end, we can dovetail in some of the Siemens stuff with a lot of the other products that Josh has and Ponton has, and the expertise that Ponton and Siemens work together with. So thank you everyone for that. I think next slide, please. Siemens Process Automation Overview. So Siemens Instrumentation, that's where we, Sean and I work. We're under the Process Automation umbrella. Just kind of a quick note, Siemens engineering management level, right? We have products for design such as Comos Plant Engineering and different things like that, on down to the next level as far as operational control with our distributed control system, our Somatic PCS7, our newer guy, the PCS7 Neo, which is a web-based system, on down to the field level in our analytic products, our process instrumentation, right? Our process instrumentation, getting a lot more of the industrial Internet of Things, or IIoT. One of our pressure products, our P420, is one that covers that, and some enhanced data logging and some nice features that we can do to get you more data. But that's us. That's us, Siemens as a whole, as far as this division. Ponton has other parts of Siemens as far as drives and different things like that, and really our areas of expertise on the right there as well. We really our control guys are tops in chemical. We do really well in the instrumentation side in water or wastewater, and really have seen it all in these different industries. So just Siemens as a note there. So next slide, please. So the agenda for today, so what is pressure? What are some different applications? What are the installations, considerations you have for that? And what are the advanced features and capabilities? And then the products that are over on the left, what fits my application? Is it a differential? Is it a gauge? Is it one of your more specific, lower cost, pre-range guys there, kind of in the middle there? So like I said, I'm kind of going to go over some quick basics, and Sean's going to get into some really good application considerations, and then we can talk towards the end. So next slide, please. Two angles to consider today. I have an application that requires a measurement. Okay, well, now I have one that measurement is pressure, so I know I need a pressure transmitter. How do I navigate all the different options there, right? What do I do? How do I select it? It is pretty simple once you realize you don't have to get overwhelmed with all those options available. And again, Sean's really going to cover that well. The guy there on the left, I know Sean's fond of that, as I am as well. It's not just good marketing. The superhero pressure transmitter guy, really, you can do a ton of things in your process with taking a pressure measurement, and again, we'll cover that, whether it be level or flow, etc. So next slide, please. So where to use pressure transmitters? Well, in pressure applications. So next slide. What is pressure? Well, pressure is everywhere. It's atmospheric, or it's in our process, and that that illustration over there on the right is essentially your atmospheric pressure, right? It's columns of molecules of air acting on your head, being pulled down by gravity. Now, over on the left there, a little bit of that picture, it's the same column of air acting on you, but you're at altitude. Perhaps you have less molecules acting on you. Perhaps you have changes in weather. All these affect the pressure measurement, right? Now, your high and your low front coming in, giving you a little bit of rain is probably only going to change your pressure measurement in millimeters of mercury or inches in the water column, not a bunch of pounds per square inch. But this is important to really remember as we get into the nuances, which matter for a lot of pressure applications and a lot of different processes. So this is one where I don't always put it this way, but I wish I did. All right, all pressure measurements are differential measurements, meaning they all reference another measurement. It's not just one thing pushing on a diaphragm. These predefined references, you have gauge and absolute. So for gauge, you have the atmospheric pressure. For absolute, you have no molecules, absolute zero, and then you have a user-defined reference, which is your differential. So next slide, please. Gauge pressure measurement, right? So process versus ambient conditions under atmospheric pressure. If you have process above atmospheric, and like I said, in a lot of those times, I think of it as 14.7 psi. But Sean really will illustrate the nuances going forward. So for gauge pressure, your reference is atmospheric. If you have a positive reading, right, you're above atmospheric pressure. If you have a negative reading, you're starting to pull a vacuum. You're starting to get below that atmospheric pressure, below that 14.7, right? So it brings it on down to that next guy there. Negative gauge pressure reading indicates that you are pulling a vacuum. And this is illustrated on some future slides, and I've heard Sean get it in the past. A lot of people, myself included, still to this day, over 10 years of doing this, I think absolute when I hear vacuum, and then I correct myself. So if you want to measure a vacuum, you really need a gauge pressure measurement because you're measuring below that atmospheric reference. If you try to measure a vacuum with an absolute, you're not going to be too successful because you can't have less than zero matter or less than zero molecules. So next slide, please. Which brings us to absolute pressure, and I believe the next slide will be kind of the application. So as we said earlier, your pressure is all to a reference point, right? So your absolute pressure, your reference is a full-on vacuum that is a fixed reference point and that does not change, right? Your gauge reference is dynamic. Your atmospheric is dynamic, as I mentioned, although it may be small, right? It may be a couple inches in the water column due to some weather conditions. It does change, right? So absolute pressure, full vacuum, fixed reference point, regardless of what's going on. And to reiterate, full vacuum, the absence of matter, no molecules means no pressure, right? So you can't have less than no molecules. So again, keep in mind that absolute pressure really is not designed to measure your vacuum. When you're pulling a vacuum, you want to measure it with gauge. But the next slide covers absolute applications a little bit better. So what does it mean? When do you want to use absolute pressure? That's when you want to isolate the process from outside changes in ambient conditions, or two different locations globally, right? So the illustration over on the right is pretty good as far as it gives an indication that altitude and boiling point. The boiling point of a fluid depends on your altitude as well as your pressure, right? Is a direct relationship. A lower pressure indicates a lower, a lower boiling point of that fluid. So if you're batching, if you're producing something, it reacts differently at altitude. So that said, if you can take that variable out of the equation and use absolute, where you're based on your absolute pressure measurement, that really helps you out. Say food and bev and pharma are two big examples, right? If you have Coors in Golden, Colorado, and you're making beer, and then you're making one down in Louisiana at sea level, and you want your Coors original to taste the same, consistency of product is important. You might want to use your absolute pressure. Well, that's kind of a fun example. Think pharma, on the other hand, right, where a cancer drug being manufactured in New Jersey and a cancer drug being manufactured in Zurich really need to be the same and be effective. So rather than compensating for atmosphere and everything else like that, if you really you approach it from a use of absolute pressure standpoint, it helps you in tightening those controls on your process. So and then conditions controlled for uniform measurements. Like I said, compensations are not required, and really optimized for batch processes. Like I said, using that batch of a drug, for instance. So, next slide, please. And I believe this is the last one for me, right? So what is pressure? The last one we're covering is differential pressure, right? So gauge was the first one, where your reference is your atmosphere. Your absolute was your second one, where your reference is full vacuum, zero molecules, absence of matter. And differential pressure is your final one, which is your user defined, your high side versus your low side. And DP really gets into what we can do with pressure transmitters, all the installed base to measure flow and level and things like that. So you want to measure the difference across either side of a diaphragm, and then the process pressure that will cancel each other out. So really keep in mind that even if your pipe there is at 2,000 psi, it doesn't matter if that obstruction in the middle is only causing a drop in the water column of 80 inches in the water column. Sean will get into it. He uses a fixed volume. I think of conservation of momentum in this illustration here, but you got to think when you're measuring flow, that's relative to the square root of the velocity. So if you're measuring flow, go ahead and get yourself a square root curve. But that's just my flow nerdiness coming out. Sean's going to cover that much better in a couple slides. But DP is really the applications are endless for differential pressure. So that said, I think it's Sean's turn now, and thank you guys so much.
Thanks, Cole. All right, just a real quick intro. I'm Sean McNutt. I am the product manager for pressure and temperature for the US. So I've been doing this for about 15 years, started off in tech support and application engineering. So I'm still learning something every day, because pressure applications are all over the place. There's so much they can do, so many different considerations to take when you're designing or implementing a pressure transmitter. But really understanding how they work is how I've always thought was the best approach. If you understand how it works, it's a lot easier to apply it, because you can really kind of visualize in your head what it's doing. And the first kind of application Cole covered here, your pressure applications, those are the obvious ones. You want to measure pressure, use a pressure transmitter. Now, what's not so obvious, which if you're in the industry, it's pretty obvious, but for other people it may not be, level applications are really common installations for pressure transmitters. In fact, pressure is the most common technology in the field used for measuring level, and it can be used in either vented or pressurized vessels. One quick note is that it really only works with liquids. You can't use pressure transmitters to measure level of solids. Solids are kind of self-supporting. You can get air pockets and cavities and things like that, where the solids won't directly exert a pressure on a point in your vessel that a liquid would. So how do you measure level using pressure? And use the concept of hydrostatic pressure. And what hydrostatic pressure is it's the pressure exerted by a fluid due to gravity. And you can visualize that in the real world, in a pool or a submarine, or when you're taking a drive, even up to the top of a mountain. You feel a pressure drop in your ear. Your inner ear has that equilibrium to the atmospheric pressures, and when those outside pressures change, you can feel it in your ear. Now, if you hold your nose and blow out, it equalizes that pressure. But you'll notice the higher up in a mountain you go, or the deeper down in a pool you go, you can feel those pressures pushing in or going the other way. And that is technically hydrostatic pressure. And those pressures change based on specific gravity. So the higher specific gravity or density a liquid has, the more pressure it will exert given a certain height. And what makes it really easy to measure using pressure is that pressure exerted from the fluid has a direct linear relationship to level. So if your level goes up 50%, your pressure is going to go up 50%. And that makes it really easy to scale and infer what your physical level reading is from a pressure reading. It's so common, in fact, that there's measurement units for pressure that are defined by various fluids. Cole mentioned inches of water column. So that is the equivalent pressure that 1 inch of water above you would exert. And the same applies for feet of water, millimeters of mercury, inches of mercury. All these are pressures based on the level or the hydrostatic pressure exerted by that height of a fluid column. So measuring level in a tank, one of the most common is an open tank. So you have atmosphere pushing on the top of the tank, and then you have the liquid filling that vessel or tank. And then when you put a transmitter at the bottom, you're measuring that fluid exerted in the tank, and atmospheric pressures kind of cancel itself out. This means you would use a gauge pressure transmitter. So you have that reference to the gauge measurement on one side of your pressure transmitter, and that cancels out all those atmospheric conditions. A low front moves in. Time of day even can make a change in your ambient conditions, where if you were to have a sealed tank or even an absolute transmitter, you may see almost like a sine wave based on a 24-hour cycle, where you'd have a peak at noon, and then when it gets the coldest point during the day or at night, you would have a little dip just based on those changing ambient conditions. But if you make those changing conditions your reference, then you don't need to worry about them. And a gauge measurement on a tank is as easy as it can get. The tough part is installing if your tank's already full. And that's where some of those isolation valves and things that Josh was talking about at the beginning really come in handy. Now, open tank, just put a pressure transmitter at the bottom. It's pretty simple. Now, if you have a closed tank, say you're maybe dairy storage where you have a nitrogen head, or a steam boiler where you've got a pressurized steam on the top with water down in the bottom boiling up, you can't use a gauge transmitter since atmosphere really doesn't have any effect on the inside of the tank because it's all sealed up and pressurized. You're going to need a differential pressure transmitter. And what that lets you do is you define your reference where one of the pressures measurements is at the top of the tank and the other one's at the bottom. So think about sitting down at the bottom of this tank. You would feel both the pressures of the liquid as well as the pressures from the gas header or whatever is on the steam that's pressurized on top of that tank. And if you can measure what that steam is, or the header with the other side of the pressure transmitter, what that effectively does is it cancels out that excess pressure, the parts that aren't really your hydrostatic measurement. And by canceling that out, all you're left with is hydrostatic, and you get that, again, direct one-to-one relationship between pressure and level. Now, that's really easy to visualize a tank, but say you've got something like a well or a pond and you want to measure that. You can't really mount a pressure transmitter on the side of a well unless you're going way down deep, and I don't really know how you would install that. This is where submersible transmitters come in. And submersible transmitters are really the same technology as a gauge transmitter, except they use a special cabling or cord that lets you suspend the transmitter over the well and drop it down and measure just how much liquid is up above it. You do still need an atmospheric reference. I mentioned it is a gauge measurement, so that cabling is where this comes in handy. You not only have your twisted pair wire for signal and power for the electronics, but you also have a little tube in there, a little capillary that up at the terminal box mounted outside of the tank will be mounted, and that is where your atmospheric reference will sit. So you want to keep that box dry and clean, and then changes in ambient conditions are not going to affect your level reading. One of the coolest applications I saw for these submersible transmitters were in a golf course, where they wanted to make sure the pond in the middle of the golf course was always at the right level and automate that, but they didn't want to mount an ultrasonic transducer or a radar, something that was sitting up above the pond level. But they wanted something to come back to the control room. So they took one of these submersible transmitters and lassoed it out almost and chucked it out into the middle of the pond. It sank down to the bottom, and then under the silt, they ran this cable back up to a little control room that was sitting right next to it. So they were able to get a reading that was kind of invisible to the patrons of that golf course. So not always the first thing you think of, but the applications for these measurements are really everywhere you can even come across. Now, beyond level, pressure transmitters are very commonly used for flow. Again, they're actually the most common technology in the field for measuring flow rates. And this is going to be volumetric flow, And the catch here is that when you're using for flow measurement, it always has to be a differential. And a differential pressure transmitter by itself doesn't do a whole lot. So you're going to have to pair that with what we call a primary flow element. And these are things like orifice plates, venturi tubes, pitot tubes, things like that. And what these all really do is they add a restriction into your pipe. And volumetric flow is always the same no matter where you are in a pipe. So by adding a restriction, the same amount of fluid has to flow through a smaller area as it would the larger area of the pipe. So for that same volumetric flow to happen, it needs to speed up. And you can kind of visualize that when you put your thumb over the edge of a hose. Your flow rate's going to be the same, but when you restrict the opening at the end of that hose, the fluid has to move a whole lot faster to get out of that smaller opening. And because it's moving faster, you have more force, and that lets you squirt somebody that's sunbathing across the yard or something like that. But that volumetric flow rate is going to be the same, but you have an increase in velocity, and that gives you a decrease in pressure. And you can actually feel that as well. So on your thumb, you feel that higher pressure acting on the back of your thumb. And the cool thing about these primary flow elements is that you can actually measure that pressure drop across the restriction you've put in your pipe. And that has another direct relationship to volumetric flow. It's not a linear, so it's not quite as easy as measuring level. It's going to be a square root relationship. So if you take the square root of the pressure and correlate that to a flow rate, you can get an exact volumetric flow rate. With modern transmitters today, there's application switches right in the transmitter. You can either enable them with software, or in the case of the P320, P420 Siemens pressure transmitters, you can just get in there with the push buttons, hit a couple options in the menu, and now your transmitter is already set up with the square root relationship, and you can display flow units right at your local display instead of pressure that you would then have to manually convert. So all these applications are out there for using a pressure transmitter. So maybe we've got a level measurement or a flow, and we know we want to use pressure for our installation, but there's so many out there. I mean, the pressure section of our catalog is probably about 200 pages long. Every vendor has tons of them, and usually broken out into different chapters and categories, and it gets really overwhelming really quickly. So we can kind of narrow those things down to what are some of the top considerations? What do we really need to focus on when we want a pressure transmitter? First being the type of application, and that's what we talked about already, flow, level, differential. It helps you get an idea of what your requirements are going to be. The other being communications. So we're taking this measurement, how are we getting it back? What are we doing with it? If you can get something like the pressure range, how much pressure drop across the orifice plate, what the height of your fluid is compared with the density or specific gravity, we can get a pressure range from that. Most of the time, this is going to be defined on something like an ISA data sheet coming from an engineering firm. A lot of these parameters are already defined. Otherwise, you can provide some of this data, and we can do a lot of those calculations for you. Things like process connections, process conditions, static pressures, ambient pressures and temperatures, they can all have an effect on which pressure transmitter you need to pick. So Siemens has created a pressure application questionnaire where you can fill out some of these basic details, and from there we can get you going with the proper pressure transmitter selection. And ISA data sheets are just another way to get that data communicated to either a vendor or an engineering firm or your end user. So communications are how we're getting that reading. And the most common by far is going to be purely analog gauges. And they're common in the field, but not so common for process control because obviously there's no communications. It's simply a visual indicator. You walk out there and see what the pressure is, and that's really it. The step above that would be your analog but electronic style transducers. They tend to be simple devices, a few $100s, where you're doing that same pressure measurement, but you're converting that into an electrical signal. And they can be current or voltage outputs, or sometimes not even a direct pressure measurement, but something based on a switch, like a relay. Now, where we really play well is in the smart transmitters. We have the Siemens has the lower end, the simple pressure transducers, but smart transmitters is where you're going to get all the user-friendly features, the expanded capability, and really get you kind of a one-size-fits-all family. And what they give you is something like a scalable output, where if you have a simple transducer, you buy one that's 0 to 15 psi, that's what your output's always going to be scaled for. With a smart transducer or transmitter, you can scale that yourself and kind of tailor it for your specific application. Along with that scaling, you get diagnostics and other smarts, things that are built into the transmitter, where you're doing some signal analysis, some process analysis, and then even using the digital communications, sending some of that data back to your control room, where you get alarms and status updates. And of course, HART, Profibus, Foundation Field Bus, those are some of the sample digital communication protocols. So if we know how we're getting that data back to us, we want to know how much pressure are we actually measuring. Kind of like how you wouldn't use a meat thermometer to see if you have a fever. And if you're trying to measure walking speed, a car speedometer is probably not the best idea. You want to make sure you have the right transmitter for your pressure range. And the way you look at that, the terminology in the industry is maximum measuring range and set span. So maximum measuring range is the capability of your transmitter. For example, a 200 PSI transmitter as what it's capable of measuring. Set span is what you're actually, the range of the pressure you're really measuring. So maybe you're only measuring 0 to 120 PSI, where you're not using that full capability of the transmitter, but you're using a pretty good chunk of it. And the ratio between that transmitter's max capability and what you're really using it for, that ratio is called turn down. And turn down becomes really important when we start looking at things like accuracy and performance, because as turn down goes up, the higher turn down you're using, the lower that performance would be. And that performance, the most obvious thing is going to be your accuracy. So reference accuracy is what everybody's going to have published. It's going to be the kind of like data sheet bingo. One of my German colleagues told me, where you're looking for a number and it may not be real world, but that's what you or your customer really want to use. And reference accuracy is great, and everyone tries to get the best one out there, but it's not really a good indicator of how a transmitter is going to work in the real world. Reference accuracy is defined by ideal conditions. So 14.7 psi at 60 degrees Fahrenheit, using only stainless steel materials and room air for your measurement, and all these asterisks behind that reference accuracy and what that means. So to get a better idea of how your transmitter is going to perform, you want to look at total performance, and that's going to be a real world indicator of how that transmitter is going to go. Siemens, on our process industry portal, we have an accuracy calculator. It's an Excel file, because the formulas behind this are really not friendly. They're in our catalog. If you want to be ambitious, you can get all the different equations where you can plug in your temperatures and your turn down ratios and get all the different specific values, where we have an Excel sheet for you that can do all that math for you. And that combines things like the effects of ambient pressures and temperatures. As ambient temperatures change, metals behave a little differently. The fill fluids inside a pressure transmitter expand and contract. So there's some influences on your pressure reading based on things that are not directly related to your process. So by combining all of these things together, you can get an idea of how your transmitter is really going to work. And turn down is just one factor in those equations, but it's directly tied to how that transmitter is really going to perform. Now, personally, I've been doing this for a while. I don't like to recommend a turn down higher than 10 to 1. Once you get beyond 10 to 1, you start seeing some pretty decent effects from temperature swings, pressure swings, things like that. So you don't want to use a transmitter for less than a tenth of what it's been designed for. Now, with the latest generation, you can actually use a turn down of 5 to 1 and still meet the published accuracies. So with that reference accuracy value, as long as you're within a 5 to 1 turn down ratio, you don't really need to do any math. You can stick with those published numbers out of the catalog. And as far as telling you how much is enough, that's really up to the process. If you're good with a 0.25%, then you could probably deal with a 20 to 1 turn down. But if you need less than 0.1% accuracy or even better, you're really going to have to look at how that transmitter is going to behave in the real world. Now, as a user of transmitters, this is where things start to get a little more interesting, where the things that make your life easier. These are the advanced features and extras, like what can your transmitter do for you today? And these can be things like local displays, where you don't need to hook up a current reader and then do some scaling on your back of an envelope or in your catalog or calculator. It just gives you the value right there without having to go back to the control room or do any math. And with new transmitters, not only do you have the process values, but you can get some diagnostics. You'll see kind of the grayed out at the bottom of the display here in the corner, some status icons. And these are a NEMOR standard. NEMOR is a collection of German companies, chemical companies, that have these standards that manufacturers must abide by. And I know we're not German and we're not all chemical, but the thing is these icons actually can be useful outside of those industries. So if you walked up to a transmitter and you saw a big X on the measurement, that gives you a pretty good idea that something's wrong. Or if you see the one that has a wrench or an oil can, that's going to let you know that you need to do some sort of maintenance. Maybe a calibration interval has exceeded, or your pressure's too high and it's beyond the capability of your transmitter measuring it accurately. So you would see those kind of indications right on the display without having to hook up a computer and get some of those diagnostic values out of it. Now, as far as configuring your transmitter, it can be made really easily with onboard push buttons. So the P320 and P420 from Siemens have magnetic push buttons right at the top of the transmitter. And by using these, you can dive through all the text-driven menus that let you set up things like your pressure range, your application, whether it's flow or level. And you can do all that without having to hook up software or hardware. And since there are magnetic buttons, you don't need to worry about it being rainy or in a hazardous area, because you can just flip open that lid and you know that you're not actually opening any path into your internal electronics. You don't need to declassify an area or make sure the inside stays dry because the buttons are completely separated from the sensitive electronic bits of the transmitter. Now, of course, you don't need to use the push buttons. You can hook up remotely from your control room with a Hart handheld or some other process device software. And then you have access to things like level measurement, volume measurement, flow measurement. And that's all scalable right in the display, so you don't need to do conversion yourself. Now, this slide I can talk all day on. I actually teach a full day pressure training class. These are just the other things to consider when you're connecting to a process. So I'm just going to hit the highlights, but I mean, we could really go pretty deep into these considerations. But when you're connecting to the process, you're thinking about the parts that are going to be touching the process. So wetted parts become a concern. Stainless steel is going to be the standard, but you can get things like tantalum for measuring acidic applications, gold if you're trying to measure hydrogen, or even into some of the Teflon-coated diaphragms for sludge and slurry that may have some sticky properties. You want to make sure that diaphragm stays clean. The connections, how you're actually physically connecting to the process, are important. So manifolds and fittings, things that allow you to separate the transmitter from the process for calibration, for service, verification, things like that. But also how to remove the transmitter from the process just for the transmitter safety, I guess. Diaphragm seals, where if you have something that could clog, you may need a diaphragm seal to remove the transmitter and eliminate that possibility of clogging. Or even high temperature. You can use diaphragm seals to remove a transmitter from being directly mounted to a steam line, let's say, or hot wax is an example I use because say wax is too hot for your transmitter, the transmitter can see temperatures up to 212 degrees right at the sensing diaphragm. But maybe hot wax is 400 degrees. So you don't want to cook your transmitter. So you move your transmitter a little bit further away and you put some piping in between. But as wax cools, it turns into a solid. So your piping isn't going to transmit a pressure very well. So in that case, you would need a diaphragm seal, something that gives you a bridge between your process and the transmitter. Process temperatures, like I just mentioned, are a concern. Seals can be used for that. Honestly, we try to eliminate seals wherever we can. Of course, they make Siemens more money, they make Ponton more money, everything like that. But diaphragm seals add to the price and reduce the accuracy. So if you're only worried about high temperatures, impulse line is great. You just get some 1/4 inch or 1/2 inch tubing, and then you remove the transmitter remotely, and you're connecting it with this empty impulse line. And the rule of thumb is for every foot of uninsulated tubing, you're going to drop that process temperature about 50 degrees. So if you're trying to take a 300-degree measurement, only 2 feet of tubing is going to be required to protect your transmitter there. In the long run, it's going to save you money, and it's going to give you a transmitter that performs at its optimum. So it's always the way we try to go, is eliminating those diaphragm seals. But if you need them, we can get you those as well. Process pressures are, of course, important because we're measuring pressure. But what may not be so obvious is the static pressures and overpressure protections. So if you've got a gauge measurement, the typical rule of thumb is they can handle about a 50% to 100% overpressure. So say for a 200 PSI transmitter, a spike of 400 PSI probably isn't going to break it. But if you might have spikes of thousands and things like that, you may need to either look at a larger rated transmitter or some other considerations. Static pressures come into play where differential pressure measurements are concerned. Cole's example was that 2000 PSI in that filter, where you have 2000 PSI in your process, but maybe you're only measuring 1 or 2 in that differential. You need to make sure that all the bolts in your flanges or holding the transmitter together are rated for those process pressures. And that's why we ask things in those application data sheets is what is your process pressure? Beyond what are you measuring, we want to know a little bit more to make sure you get the transmitter that's going to suit your application the best. And then mounting position and location. That's just simple mechanical installation. If you're measuring pressure in a liquid line, you want to have your pressure transmitter mounted below the pipe. And that's just so air bubbles can go back into your process. And the opposite's true for measuring gas. So if you're measuring measurement of a gas line or steam or something like that, you want your transmitter mounted at the top. So any condensation, instead of collecting at your transmitter and causing a false pressure reading, any condensation is going to drip right back into your process. So things like that are another consideration. Case by case, you could have very different answers. So just something to keep in mind, where am I mounting this thing? How am I getting there? You want to make sure there's not too many dips and bends where things like bubbles and condensation can accumulate. Did a quick overview of our portfolio at Siemens. At the, I guess I don't want to say the lower end, but it is the lower end, is the transducers. That's the submersible, the fixed range. And at the super high range, we have the P500, which is kind of like the, I don't know, I always call it like the Halo car, where Acura makes the NSX, which is a really powerful supercar. But most people don't need that kind of performance, and people that kind of want it, a lot of them can't afford it. It's basically just a transmitter out there saying we can do a really fast, really accurate measurement. The P320, P420 notches in right below that. And that's going to be 99% of the applications out there can be met by that family of transmitters. And the big difference between the two is a slight bump in reference accuracy in the P420, but the P420 also has a digitalization layer where it has a built-in trend logger where it's going to store 1,500 data points. And if you're hooked up to some cloud-based data collection service, you can pull out some of that data and see with some operating hour stamps, what's my pressure doing? Has it been increasing? Was there a big spike last week? Something like that. And that's all going to be stored right in the device. And that's the difference between the two. But that P320, P420 family covers all of the transmitters we've been talking about. It's going to give you your gauge, your absolute, your differential for level, flow, and pressure measurement. So the P320, 420 is definitely the way to go. It's an easy starting point. And some quick highlights of that specific transmitter. The big one I always talk about is that display and the push buttons, because as someone that goes out there and likes to touch devices and play with them, having push buttons, having a view right into what the device is doing makes that a lot easier. And Siemens devices have a new platform. We're calling it the TwoWire platform, where our new level devices, the radar and the new ultrasonic transducers, the new valve positioner, and then this new pressure and the upcoming temperature transmitter They all use the same display module. So if you know how to use one with the 4 buttons, you'll know exactly how to use the other one. Of course, the text in the menus is going to be a little different. You're not going to have RTD selection in a pressure transmitter, but the general layout and look and feel is going to be exactly the same. Their latest and greatest communications with Heart 7 have a fast response time in them. And then kind of unique to this device, it's actually a patented feature, is the remote startup for SIL commissioning, where typically with SIL devices for safety, you have to go out to each device and commission them manually. With the P320 rated for SIL, you can do all that commissioning directly from the control room, and that's because of a special heart trip. Oh, I can't talk today. A special heart chip that basically gives you a digital fingerprint, and it's a handshake between your control room and your device that is certified to be for SIL operation. So it saves you some time for commissioning and startup. So to wrap up here, the biggest thing with a pressure transmitter is there's always 2 sides of selecting that transmitter. On one side, you have someone that's defining the process requirements, where my tank is this tall and my pipe is at this pressure and the process is at this temperature, and people are defining what that process needs. And on the other hand, you have the sales guys and the manufacturers that are trying to meet those requirements. Now, if you have a transmitter that needs to be 68 psi measurement at whatever temperature, odds are you're not going to find one that's exactly that pressure range or exactly that temperature design. So that's where that communication between the manufacturer or a sales guy and the end user are important, where we get the best fit for that specific application. Now in that application, we're going to talk about what are you measuring? Is it a liquid? Is it gas? Is it steam? Is it for flow? How are we measuring it? Do we want to measure with diaphragm seals? Do we want to measure with some shutoff valves in between? And how are we connecting that? What's the physical thing? So those are just some talking points between the end user and whoever's supplying that transmitter. And the other big one that people tend to get hung up on is the performance considerations, where they're looking at that published specified accuracy in the catalog and think that they're automatically going to get that. And some of the time, actually most of the time, you probably will. But there's going to be some cases where you need to make some, I guess, considerations or give up some leeway for the transmitter, just because you can't get that accuracy out of that physical installation. However, there's ways to improve it. And the accuracy in your process also helps you determine your calibration interval. So we've got a published spec and a published drift rate, and people will be talking about how often do I need to calibrate my device? And the real question is, how accurate do you need your transmitter to be? So if you know how much leeway you can have in your process, that'll easily define calibration intervals and the transmitter required for that application. So that was me talking for a while. I'd like to, I guess, open it up for questions, turn it back over to Cole and Josh, and kind of give an open forum here and see if we have questions or comments based on what we've talked about today.
All right, thank you. And if anybody out there has any questions, please use the Q&A button on your left of your screen. Feel free to write it in. Currently, we don't have any, but if anybody wants to ask a question, feel free. We'll stick around for a minute, and I'll read any that come in. Other than that, we'll then appreciate everybody sticking around.
Yeah, thank you guys so much for your time and attention. But yeah, we're here for the next couple of minutes if any questions.
Here we go. So for a closed tank with an agitator, how good is a differential pressure transmitter?
The easy answer is it depends. I know that's not the answer you want to hear, but the big thing with an agitator is going to be I guess the waves or pressure pulses being pushed against that diaphragm. So you've got a measuring diaphragm in there, and if it's directly flush mounted to the side of the tank, If you have a decent amount of I guess, agitation, for lack of a better word there, you could see some pulses in pressure. Some ways around that would be remove it from the process just a little bit with an extension or a standoff. Most flange connections on the side of a tank aren't going to be flush mounted to the inside. So you could have a 2 or a 3 inch kind of offset from that tank wall. And just that little bit of offset will give you a good buffer to eliminate some of that. And even with some agitation, you can still get a pretty good trend line. The transmitters have built-in signal damping. So by default, they're at maybe 0.1 or 0.2 seconds, where it's kind of like a rolling average over a small time. You can set that down to 0 if you really want to capture any pressure spikes. But for something like an agitator, I may bump that up to a second. You can go all the way up to 100 seconds, but I think that's kind of crazy. But if you are seeing some noise because of those pulses, just increasing the damping of that pressure reading will filter out a lot of that pulsation from an agitator.
Perfect. Will any of the pressure sensing devices include IO-Link?
Not at the moment. There are talks about that in the next, adding that capability. We're still probably years away for IO-Link. To get that, you'd probably have to look at something like an adapter for heart that can convert to that.
Okay.
They can take the heart signal or the analog signal and then convert to the other technology.
Great. That is the last of our questions so far. So I think we'll wrap it up. If anybody else has any questions, feel free to reach out to me. My number is, reach our office at 714-998-9073, or you can always reach us at our info@pontonind.com email address. Feel free to shoot us an email. And thanks, Cole and Sean, for all your help today and presenting today.
Yeah, thank you so much. And if you guys are going to get to write that down, I can always forward stuff to Josh as well. So thank you very much, everyone.
Thank you.